Now let's talk about the impact of variance on including unnecessary variables. So let me say, beta 1 hat with a little superscript 1 to be equal to x1 transpose x1 inverse x1 transpose y. So it's the model fit with just x1 in the model. It's the beta 1 fit with just x1 in the model. And let me let beta 1 hat with a little 2 in it be equal to the beta 1 hat I get when including the x2 variables in the fit. And so recall, one way I could write this is I could write this as e x1 given x2, e x1 given x2, the transpose up there, inverse e x1 given x2, e y given x2, where e a given b in this case, well, let me just write this out. E x1 given x2 is just I minus the hat matrix for x2 times x1, and E y given x2 is just I minus the hat matrix for x2 times y. So these are just the residuals of x1 having removed all linear association with x2 and y having removed all linear association with x2. Now let's look, we know that the variance of beta 1 hat 1 works out regardless of what is the true model, even if there's an x3 that we're missing, is just x1 transpose x1 inverse times sigma squared. Now let's look at the variance of beta hat 1 fit under model 2. Okay, well, this is going to take some doing. So this term, these collection of terms, are not random, so I can pull them out. That's e x1 given x2 transpose e x1 given x2 inverse e x1, oh, I'm missing a transpose there, e x1 given x2 transpose times the variance of this guy. Okay, and I'm just going to write out that variance. That's I minus hx2 times sigma squared. I'm going to put the sigma squared just for convenience sake up front. Sigma squared, and then times the transpose of all this other stuff. E x1 given x2, e x1 given x2 transpose e x1 given x2 inverse. Okay. Now let me look just at this term right here. If I were to take e x1 given x2, and if I were to multiply it by another I minus hx2, I don't change anything because I minus hx2 is idempotent. Okay, so I can write this out as sigma squared times e x1 given x2. So just to remind ourselves, if I take this and multiply it by, if I take that and multiply it by e x1 given x2, well, e x1 given x2, if I circle it up here, right, it's just I minus h of x2 times x1. So multiplying it by another I minus h of x2 doesn't do anything. This is effectively just saying if I project onto the linear space spanned by the columns of x2, and then I'm already in I'm already in that residual space. Projecting again doesn't do anything. Okay, so let's see. So there's this term inverse, then e x1 given x2 transpose e x1 given x2, e x1 given x2 transpose, and I hope you kind of see where I'm going with this. So this and that cancel, and I see that my variance of beta 2, beta 1 hat is just now, why did I write that? My variance of beta 1 hat fit under model 2 is just this. Okay. I'm going to need some more room. Now let me write out for a particular linear combination of the betas. Let me write out variance of Q beta 1 Q transpose beta 1 hat fit under model 2. Okay, that's equal to Q transpose variance beta 1 hat fit under model 2 times Q, which is equal to this residual variance here. This variance up here, right? E x1 given x2 transpose E x1 given x2 inverse times Q. It's interesting to note, by the way, that this X transpose X matrix is basically just the variance in our design matrix, the variance matrix. It's off by a factor, but it's just basically that variance. Well, it is interesting to note that if we include X2 in the model, we get that same variance. We just have removed all the linear associations with X2. So if this variance would be Q transpose X1 inverse Q, okay? And so this variance gets replaced with basically the same variance, but with all the linear association with X2 removed. Okay, so I find that very pleasant. Okay, now let's keep working on this a little bit. So this is Q transpose, and then this I can write out as X1 I minus HX2 times X1, X1 transpose I minus HX2 X1 inverse times Q, which I can write as Q transpose X1 minus X1 transpose HX2 X1 inverse times Q. Okay, now this inverse is kind of a complicated inverse, but via the Woodbury theorem, okay, which we used when we're deriving the press residuals, I can write this out as X1 transpose X1 inverse minus, let's just say W. Okay, and W is a positive definite matrix. Plus W, where W is a positive definite matrix. So look up the Woodbury theorem, okay, and see when I have a pattern matrix exactly like this, what my inverse works out to be, and that you get a positive definite matrix there, okay? So now what I can say, okay, that this is equal to Q transpose X1 inverse plus Q plus Q transpose WQ, where Q transpose WQ, where W is a positive definite matrix, or at least positive semi-definite matrix. So I can say that this is greater than or equal to Q transpose X1 inverse Q, okay? Which is equal to the variance of beta 1 fit under model 1 hat, Q transpose times beta 1, okay? So what we've shown is that the variance of Q transpose beta 1 fit under model 2 hat is always greater than or equal to the variance of Q transpose beta 1 hat fit under model 1. Okay? Now that is a startling result, I think, because it's basically saying, and notice at no point I don't have to indicate what model I'm assuming is true in my variance. It doesn't matter. Model 1 could be 2, Model 2 could be true, or any other model could be true. What I'm saying is the mere act of including regressors into a regression model necessarily increases the variance of the standard errors. Okay, so if I have a treatment effect and I include additional regressors, I am necessarily going to increase the variability in those standard errors, in the standard error for that treatment effect. And that makes sense because remember, our standard error has in the denominator, effectively in the denominator, the variability in the x's. So if I remove variability in the x's by including extra regressors, because remember the way in which we look at regression is if we include extra regressors, we in essence regress those out of all the other regressors in the response. Okay, so that's going to decrease for variability in my regressors. That variability is in the denominator, so it's going to inflate the variance. So no matter what model is true, whether I'm fitting the correct model or the incorrect model, including regressors always necessarily inflates the variance. Now, what you might be saying is, why, when I include a regressor, does my variance not necessarily go up? My standard error, when I do fit a regressor with R, why does my variance, the actual number output, not necessarily go up? And the reason for that is because this is talking about the true variance with the known sigma squared, okay? So the true variance necessarily goes up. On the other hand, what we saw was if we overfit the model, right, we got a inflated variance of the variance, okay? Our variance of the variance got bigger. So who knows what happens in that case, right? Our residual variance estimate might be too large, or it might be too small, and it might be small enough to counteract this effect. In addition, if we underfit the model, we know that we have a biased variance estimate. So what can happen when you actually plug in the numbers and get estimates means that your standard error that gets output when you include regressors may not necessarily go up. But what we do know is the true standard error necessarily has to go up. And excuse me, back here I realized I was omitting some sigma squareds. Sigma squared throughout, but that's just a scale multiple, so it doesn't change anything. Okay, so I just want to make sure everyone noticed that. So let's talk more about that, and just on the fact that I was omitting the sigma squared as a scale multiple. Both of these get multiplied by sigma squared. So when we divide them, right, we can calculate actually how much extra variance is incurred. Right, because the sigma squared will cancel out, we can calculate exactly how much extra variance is incurred by including a new regressor in the model. And that's so-called variance inflation factors. So we'll go over that next. But the fundamental point from this lecture, which I think is a very interesting point, is that the standard error, the true standard error, so let me just write true, necessarily goes up when including new covariates. Okay, and that's a startling result. I find that very startling. Regardless of what model is true, the more complicated model is true, even if that's the case, by including new covariates, even covariates that are necessary to put in the model, we're going to inflate the variance. Okay, so now let's talk about and prove things about variance inflation factors.